Okay, moving on to section 4.5. Here we're going to be solving exponential and logarithmic equations and some applications, although I think we're going to see many more applications in 4.6 in the next section. But for now, we just want to know how do we solve equations when you have exponents or logarithms. And to do that, we're going to exploit the fact that these functions, both exponential and logarithmic functions, are one-to-one. And here's effectively what that means, right? It means that when you have a to the m equals a to the n, that m and n have to be the same. When the bases are the same, the exponents are the same, right? And we've seen examples of that already, but let's do another one. Suppose we want to solve the equation, let's say 3 to the x equals 3 to the 7. Well, right? The a is 3 here, the m is x, and the n is 7. So if the bases are the same, that just tells me that the exponents have to be the same, right? Now, maybe that was a little too easy, right? So maybe you can try this one. How about 8 to the x plus 1 is equal to 4 to the x? Okay, so this one's a little bit trickier, right? And it's because you notice that the base is not the same on both sides. 8 does not equal 4, okay? Which means you cannot say that x plus 1 equals x. In fact, even if you do, you don't get a solution to that, right? This has no solution. Okay, so that's not the way to do this here. Obviously, in order to set the exponents equal, the bases have to be equal, right? However, the nice thing about this is that 8 is a power of 2, right? 8 is 2 times 2 times 2. So this is 2 to the 3. And 4 is 2 times 2, right? It's 2 to the power 2. And by the properties of exponents, right, you just multiply the exponents here, right? This is 2 to the power 3 times x plus 1. And this is going to be 2 to the power 2x. Now the bases are the same. They're both equal to 2. So now I can use this property here that says that I can take the 3x plus 1, 3 times x plus 1 rather, and that has to be the same as the other exponent, 2x, right? So I just set this exponent equal to this exponent because the bases are equal. Okay? And I think you can take it from here. You know how to solve this, right? This is just 3x plus 3 equals 2x. So in fact, you can subtract the 3x from both sides, and you get 3 is equal to negative x, or x is equal to negative 3. So yeah, so that's the solution to this. X equals negative 3. And if you might be thinking, well, can it be negative? Of course, an exponent can be negative. In fact, we can check this, right? If we plug in x equals negative 3 here, we get 8 to the power negative 3 plus 1. That's 8 to the negative 2, which is 1 over 8 squared, which is 1 over 64. So that's the left side. What about the right side? What's 4 to the power negative 3? Well, that's 1 over 4 to the positive 3. And 4 times 4 times 4 is 64. So you get 1 over 64. Those things are equal. So that convinces me that negative 3 is indeed correct. Right. So that's how this works for exponential functions. When you can get the bases to be the same, like they're both, right, both the bases here were equal to 2, then that's easy. Then you just set the exponents equal to each other. Okay, next problem. So we have 5 to the x equals 20. We want to solve that for x, right? We want to solve for x. Right. And to do this, we're going to just use the definition of the logarithm, right? So remember, this is a to the m equals n, right? Well, if you want to know what m is, you need a logarithm. M is just going to be log base a of n. So we really don't have a choice here. We have to use that. So here my m is x. My a, my base, is the number 5. So this will be a little 5 right there. And then my n is the number 20. It's on the other side, right? So there's our answer. X is just log base 5 of 20. Okay, which is not 4, right? Be careful here. 5 to the 4 is not 20. Right? Remember, x is the exponent. It's not 5 times x equals 20. Obviously, that would be 4. That's not the question. It's 5 to the power x. So you're solving for the exponent. When you're solving for an exponent, very often you need a logarithm. And that's the only way to do this one. Okay. Now, what is log base 5 of 20? So remember, we did that way back in 4.3. We can use our calculator to approximate it. Actually, here's what we can do here. Let me get rid of that first. Yeah. So this is, right, by the change of base formula, this is the log of 20 divided by the log of 5. And I'm just going to use base 10 here. Okay, log 20 over log 5. Just plug that in your calculator. And this will be approximately 1.86135, but the 5 rounds this up to a 4. So I'm going to say 1.8614. So this is to 4 decimal places. I know I didn't say that, but keep in mind that this is the exact answer, right? This is exact. And this down here is approximate. In some problems, they want the approximate. In some problems, they want the exact. In many cases, they want both. But you should know the difference, right? Okay. So let's do another one. Okay, so solve for w. E to the 2w plus 1 equals 36, right? So this is the same idea here, right? There's no way you're going to find a common base for e and 36, just like with the 5 and the 20, right? You can write 5 squared as 25, but not 20. So in fact, that's the question, right? 5 to what power is 20? Well, it's about 1.86, right? So same idea here, right? We simply want to write, we simply want to solve for this w right here, all right? And again, the way we're going to do this is to treat this as an exponential. This is a to the m equals n, right? So a is e. Remember what e is. It's about 2.7, right? It's in your calculator. M is the entire exponent. This whole thing, 2w plus 1, that's the m. And n is 36. Okay. So we know that m is just log base a of n, right? And so 2w, right, m is 2w plus 1. That's going to be log base e of n. N is 36. Okay. Now we're not quite done yet because we have to solve for w, not 2w plus 1. Oh, by the way, remember log base e is also natural log, ln. So I'm going to write this as ln of 36. Right, so subtract 1 from both sides, and you get 2w is equal to natural log of 36 minus 1, and now just divide by 2. So w is going to be the natural log of 36 minus 1 all over 2. And I know what some of you are thinking. You're thinking, hey, of course, that's just the log of 35 divided by 2. And if you're thinking that, you're way wrong here. That's not what this is. You cannot do that. So think about what we're doing here, right? We're taking the log of 36, do that first, and then take away 1, right? So if it helps, and you might want to do this, if you're tempted to subtract the 36 minus the 1, then maybe put the 36 in parentheses. We should have done that way over here. Okay, now, and the same thing is true up here for the log of 20. Now, the book doesn't do that, and I usually don't do that, but if it helps to prevent this kind of an error here, then by all means do that, right? So let's make this clear, right? So W is the natural log of 36. In fact, I'll put that in parentheses, and then minus 1, all divided by 2. Okay. So what is that approximately, right? Again, this is exact. And now we want the approximate. So on your calculator, you do natural log, ln. You don't need to change the base here, 36. So that's about 3.58 something. And when you take away 1, you get about 2.58. So the numerator is about 2.58352 something. And when you divide that by 2, you get 1.29175. Oops, so that's 1.2918. Okay, so that's the approximate. Okay, and by the way, if you did natural log of 35 divided by 2, right, just to show you that you would be wrong here, this is approximately 1.7777, and you can see that while it's somewhat close, it's really not that close. You're off by about a half, right? About 0.44 something. So no, you get the wrong answer, right? So you cannot take away 36 minus 1. It's the log of 36 first, do that first, and then subtract the 1, right? And really, the best way to write this then would have been to do this. It would have been to say W is negative 1 plus the natural log of 36 all over 2. Right? If you put the negative 1 in front, you're not tempted to subtract 36 minus 1. So maybe that would have been the best way to write the answer. But, I'm not picky. You can write it any one of these ways for the exact answer, and then this is the approximate answer. So I hope that helps. Okay, on to the next one. We want to solve 400 divided by 1 plus e to the negative x equals 350. Okay, so in this problem, of course, here's your exponential, but there's nothing to convert to a logarithm yet, right? Remember that what we're going to use eventually here is this. But we're not there yet, right? We don't have e to the negative x, right? Equals something, right? It equals n in this case, right? That would be the n here, right? So essentially, that's our first goal, to get the equation to look like this. Right? So that's going to involve a lot of algebra. So let's do that. The first thing I guess I would do is notice that this is a fraction. 400 divided by 1 plus e to the negative x, right, equals 350. So why not just get rid of the fraction, right? Multiply both sides by 1 plus e to the negative x. So do that on the right and on the left. And we do that so that we can cancel the 1 plus e to the negative x on the left. So on the left, we're just left with 400, right, times 1 equals 350 times, sorry, it's a 0, times 1 plus e to the negative x. Okay, so far? All right, so there's a couple things you could do here, right? You could just divide by the 350, because that's the opposite of multiplying. So why don't we just do that? Divide both sides by 350. I should probably use a different color, not that it matters that much, but yeah. So divide both sides by 350. Okay. So, yep, the 350 cancels on the left, or sorry, on the right side, and on the left side, you get 40 over 35, right? 40 over 35, and if you divide by 5, I guess you get 8 over 7. So this reduces to 8 over 7. And on the right, we canceled the 350s. You still have 1 plus e to the negative x. Okay. Now this is looking a lot better, right? Why don't I just switch sides? So I'll put the 1 plus e to the negative x on the left and the 8 over 7 on the right. So you can see what we want to do now. We just want to take away the 1 from both sides. So subtract 1, and that isolates the e to the negative x. Remember, that was our goal. E to the negative x equals what? So in this case, e to the negative x equals 8 over 7 minus 1, but that's 8 over 7 minus 7 over 7, which is just 1 over 7. Okay. So that's the n up here, right? The n is really just 1 over 7. Okay. So let's see. So let me just copy that down. E to the negative x equals 1 over 7. So I just brought that up here. Now we know what to do, right? Now we can convert to a logarithm. In other words, we're going to do this, right? So my a is e, my m is not x, right? M is the whole thing. It's negative x, right? And n is just 1 over 7. So m, that is negative x, equals log base e of n, which is 1 over 7. Okay, so the only thing left to do is divide by negative 1, or multiply by negative 1. I guess it doesn't matter. Multiply by negative 1, and I'll just put a negative on the right. So this will be a positive x equals negative, and remember, log base e is ln of 1 over 7. And there you go. You could write this as your answer. Negative log, natural log of 1 over 7. However, there's one more thing we can do to make this a little bit nicer. So here's what I'm going to do. I'm going to take this negative 1 in front, and since that's my p, I'm going to put that as the power. So this is going to be positive natural log of 1 over 7 to the power negative 1. So what does it mean to have an exponent of negative 1? Well, I hope you know what that means, right? If I have a to the negative 1, it just means you take 1 over a. You take the reciprocal, right? So what's the reciprocal of 1 over 7? Well, it's 1 over 7, which is just 7, right? So there's my final answer. X is just the natural log of 7. Right? And again, that's exact. Or if you want the approximate, just use your calculator. I get 1.9459. Right, and that's the approximate answer. Again, I'm using 4 decimal places. If it was 3 decimal places, you would make this 1.546. Right? If this was 2 decimal places, it would be 1.55. If it was 1 decimal place, it would just be 1.5. And if it was to the nearest whole number, it would just be 2. But again, we want to be as precise as possible. So I think 4 decimal places is usually enough, rather than doing 3 or 2 or 1. Just read the directions carefully. If it says to do 2 decimal places, just do 2. If it says to do 4, do 4. You know how picky Connect Math can be with number of decimal places. So just be aware of that. Okay, so now we want to solve log base 2 of x minus 5 equals 6. And so this is a different type of equation, right? This does not involve an exponent. It involves a logarithm, right? So now we can use this property here, that if we have the same log on both sides, that we can just cancel them out, right? Cancel out the logs. You can't divide by it. I think back in 4.3 I warned you, right? Never divide by log. Never divide by log by itself, right? You can divide by the whole thing, right? You can divide by all of this, right? But you cannot just divide by this. That makes no sense, okay? Right. So, yeah, so how do we solve this, right? So we're not going to use, we can't divide by log base 2. That's meaningless. But what we can do is just reverse the rule, right? This is log base A of n equals m. That's the same thing as n is equal to a to the power m. So if a is 2 and n is x minus 5 and m is 6, well, that means that n, that's the x minus 5, right, that has to equal a to the m, or in this case, 2 to the 6. Now be careful, you don't write 6 to the 2, right? This becomes the exponent, right? That goes into the exponent. So think of the g as a boot. It kicks the 2 to the other side, knocking the 6 into the exponent. Okay? Right, so that's what gets rid of the log. Now, we're not quite done yet because x minus 5 is equal to 2 to the 6. And 2 to the 6 is, I think it's 64. And now when you add 5 to both sides, you get 69. So that's the solution. That's what x is, right? Right? So again, I want to warn you because a lot of people have this really bad habit here of doing this, right? They just divide by log of x, log base 2, and then they have x minus 5 equals, 6 divided by log base 2. So you can add the 5, but that doesn't do anything because that's not the answer, right? The answer is 69. This is meaningless. So just be careful you don't make that mistake. Okay, another one. How about natural log of x squared minus 2x equals the natural log of 3? Well, notice that this is base e on both sides, right? It's the same base on both sides. You can write this as log base e of x squared minus 2x, and this is log base e of 3. Parentheses are optional. So as long as it's the same base on both sides, I can just drop the logs, right? You're not dividing by it, but you're just canceling them on both sides, right? That's what this up here, this thing here says you can do, right? Because logarithm is a one-to-one function, that allows me to do this. Okay, and you can take it from here because x squared minus 2x equals 3 is just a quadratic equation. You know how to solve those. Hope you can factor. Obviously, you could use the quadratic formula here, although I don't know why you'd want to do that when it's a lot easier just to factor this out. And you get your two solutions, right? X equals 3 and x equals negative 1, right? And we should check, right? I know we haven't been checking recently, but it's a good idea, right? So let's start with x equals 3. Let's check that. If I take the natural log of 3 squared minus 2 times 3, do I get the natural log of 3? Well, what's this on the left here? 3 squared is 9, and 2 times 3 is 6. Well, 9 minus 6 is 3, so of course that's equal to the natural log of 3. Whatever number that is, and not that it matters, it's what, 1.7 something? No, it's about 1.099. It's about 1.1. But whatever it is, it's the same number on both sides, right? So we know for sure that x equals 3 is correct, right? Yeah. What about negative 1? Right, so let's check that. So if I take the natural log of negative 1 squared, and then minus 2 times negative 1, is that equal to the natural log of 3? Well, remember, negative 1 times negative 1 is 1, and negative 2 times negative 1 is positive 2. So, of course, you still get log 3 on the left and log 3 on the right. So So even though this is a negative number here, and remember, you cannot take the log of -1, that's undefined for our purposes, it turns out that we didn't take the log of -1, we took the log of +3, which is fine. So you can get a negative answer for your, for your equations as long as you're not taking the log of a negative number, right? If you're taking the log of -1, then you have to, get rid of the answer there, right? But not in this case. Not in this case. In this case, everything works out perfectly, and we get two legitimate solutions here, right? They're both correct. Okay, let's try this one. This is the log of x plus the log of x minus 21 equals 2. Okay. So notice that they're both the same base on both sides, right? They're both base 10, right? Because when you don't see it, right, it's a 10. Right? So this is log base 10 of x plus the log base 10 of x minus 21, and that's all equal to 2. Right? So you might be thinking, well, just do the same thing as we did in the first problem, right? Just kick the 10 over to the other side, knocking the 2 into the exponents. Well, that doesn't quite work here. Why this 10? Right? Why not this 10? Can I kick that over? Can I do them both? So the answer is no. You can't do any of that yet, right? The rule you want to use here is as follows, right? You want to do log base a of n equals m. That becomes n equals a to the m. So notice that this is just a single logarithm. It's one logarithm. Here we have two different logarithms. So this process here of kicking the a over doesn't work when you have two of them. It only works when you have one. Right? So what do? Well, what we did in the last video, in section 4.4, we combined these down to a single logarithm, right? So since I'm running out of space, let me just move things around. Okay, so I put this down here because I want to play around with this now. So, right, so this is the log of m plus the log of n, which is the log of m times n. Right. So that's the product rule, right? Just going the other way. So now, all of this is my, well, it's my n now, my capital N down here, right? But if this bothers you, you can distribute the x, right? You can write this as log base 10 of x squared minus 21x. Right? I mean, you don't have to, but you're going to do that eventually. And that's equal to 2, right? So now we can see, right? My a is 10. My n, this is all n, right? So that's a, that's n, and this is m. So now I can convert this to an exponent, right? So my n is just x squared minus 21x, and this is going to be a, which is 10, raised to the power 2, right? So this 10 gets kicked to the other side, knocking the 2 into the exponent. All right, well, you can take it from here, right? This is still x squared minus 21x, but what's 10 squared? 10 times 10 is 100. And this is another quadratic equation, but I think you can handle that, right? Take away the 100 from both sides. And now it's in standard form. Okay, so a is 1, b is negative 21, c is negative 100. So you can use the quadratic formula if you like. I mean, that's a reasonable thing to do, but I'm gonna see if I can factor this, right? Keep in mind that factoring doesn't always work here. And when it doesn't, then you have no choice. Just use the quadratic formula. The last thing you want to do is complete the square here. That would be atrocious. I mean, it would work, but it's not pleasant, right? So what two numbers multiply to negative 100 and add to negative 21? So, right, we know it's not negative 10 and 10. That would be negative 100, but that adds to 0. So maybe we back off a little bit, right? Maybe it's, right, so one's positive, one's negative. How about 2 and 50? Right, that would be negative 48, so that doesn't work. You could do 4 and 25. And what's 4 minus 25? It's negative 21. So there you go. So that's it. Let me just make it official here. So this is going to be x plus 4 times x minus 25. So x plus 4 equals 0 gives us x equals negative 4, and x minus 25 equals 0 gives us x equals 25. So once again, we get our two solutions. Again, quadratic equation. We're not surprised we get two solutions. But just like in the last problem, don't forget to check, right? So let's, boy, I'm running out of space here. So let me check way over here. Right, so let's check negative 4 first. If we replace these x's here in the original equation with negative 4, what do we get? We get log of negative 4, right, plus the log of, what would it be, negative 4 minus 21 is negative 25, equals 2. But we can stop right here, right? The log of negative 4 and the log of negative 25 are undefined. So this doesn't work, right? So negative 4, as it turns out, in this case, is an extraneous solution. It's not really a solution, right? It's like a phantom solution. It's not really there. Okay. What about 25? Let's check that. Right. So again, 25 is positive, so you might think, well, then that has to work, but not necessarily. You really should check them both, right? So if I replace x with 25, I get the log of 25 plus the log of 25 minus 21. Well, 25 minus 21 is 4. So log of 4. But does that equal 2? Is that equal to 2? Because that's the right side here. Well, you can apply the product rule, right? The product rule says that this is the log of 25 times 4. 25 times 4 is 100. And the log base 10 of 100, well, there's two zeros. So this is equal to 2, right? Remember, 10 to the 2, not 2 to the 10, 10 to the 2 is 100. So, right, so 25 is correct, right? So that is the solution, but negative 4 is not, right? Cross it out. Or if you put it, it's wrong, right? So I would mark you wrong. I mean, you'd get half credit here because you got half the right answer. You got half the answers. But if you put negative 4, you're putting an incorrect answer. So yeah, cross that out for sure. So this has only one solution. The one solution to this equation is x equals 25. Okay. All right, let's do another. Log of 3x minus the log of 2x minus 1 equals 1. So it's the same idea as the last one, right? It's not much different, except instead of a plus, now it's a minus here. Right. So that tells me we can condense this down into a single logarithm by using the quotient rule. So this is going to be log of, in parentheses, 3x, that's my m, right, minus the log of n. So it's going to be the log of m divided by n. So the log of 3x over 2x minus 1, and that's still equal to 1. Right? Oh, and the base, of course, is still 10. Right? And so now we have this in the correct form. Right? In other words, I want to save some space here. So way down here, right, log base a of n equals m is equivalent to n is equal to a to the m. Right, so what's this equivalent to? You kick the 10 to the other side, knocking the 1 into the exponent. So 10 to the 1 is just 10. Right, so now we have to solve this equation here. And this is something you've done many times before in your intermediate algebra classes. I'll give you a nice hint here that both sides are fractions. This is 10 over 1 is still 10. So why not just cross multiply, right? Multiply 1 times 3x, and 10 times 2x minus 1. So 1 times 3x is 3x, and 10 times the whole thing, 2x minus 1, right? So this will be 3x equals 20x minus 10, right? And there's no x squared here. This is a linear equation. So I think you can take it from here. Oops. Well, yeah, that's what you're going to do next, right? Subtract the 20x. I'm going to run out of space, so can I do that up here? So 3x equals 20x minus 10. So, yep, and this next thing we do, of course, is subtract the 20x from both sides. And that gives us 3x minus 20x is negative 17x equals negative 10. So now just divide by negative 17, and we get x equals 10 over 17. Oh, maybe you want to approximate that. I mean, look, this is a rational number, so we don't need to bother dividing, but I guess it's about 0.5882. So 0.5882. Okay, so that's exact, that's approximate. Yeah, but maybe we should check, right? You never know when you get an extraneous solution. So yeah, let's check. And I guess I'll do that over here on the left. Right, so we only got one answer, and let's leave it as exact. Let's leave it as 10 over 17. If you want to plug in the approximation, that's fine. In most cases, it's not going to matter, especially for your calculator, right? Boy, I'm going to run out of space quickly here, though. Okay, so log of 3 times x, that's going to be 3 times 10 is 30, 30 over 17, minus the log of, let's see, 2 times x is 20 over 17, minus 1. 1, of course, is 17 over 17. So this is going to be log of 30 over 17 minus the log of 3 over 17. And, well, you can use the quotient rule here. This is the log of 30 divided by 17 divided by 3 over 17. But when you divide fractions, you multiply by the, reciprocal. The reciprocal of 3 over 17 is 17 over 3. Right? And fortunately, the 17s cancel. And we just end up with the log of 30 divided by 3, which is the log of 10, which is 1. And that's equal to 1, right? So that's the right side. So this is correct, right? This is correct. So the answer, right, 10 over 17. Right. And again, I would prefer you leave it like that. But read the directions. If Connect Math says to approximate to, let's say, 3 decimal places, then it's 0.588. But in most cases, we want to leave it as exact, right? So 10 over 17. Oh gosh. All right, I'll leave it at that. All right, maybe one more. Log of x plus 4 minus log of x minus 2 equals log x. Okay. So so I think in this case, and it's actually very similar to the previous one in that there's a difference here on the left. So by using the quotient rule, we can condense this down into the natural log of the fraction x plus 4 divided by x minus 2. Right? And that's still equal to the natural log of x. Notice that it's the same log on both sides. They're both base e. You can write it that way, right? Log base e of x plus 4 over x minus 2 equals log base e of just x. Right? Because log is 1 to 1, you can drop the log on both sides. You're not dividing by it, but you are dropping it. And effectively, that's kind of what happens, but remember, you can never divide by log. I said that several times already. It bears repeating because it's a very easy mistake to make. If you make it here, you lucked out because you get exactly what you would get if you divided by log. But again, that's a very bad habit, and in most problems, you're going to get the wrong answer, so don't do that. Right. But we can cancel them. And if we do that, we get this equation, x plus 4 divided by x minus 2 equals x over 1. Right. So you get another proportion. And so, yep, same thing here. You can just cross multiply. So let's do that. We get x times x minus 2 is equal to 1 times x plus 4. So multiplying this out, x squared minus 2x equals x plus 4. Gather everything on the left. So x squared minus 2x minus x minus 4 equals 0. So you get x squared minus 3x minus 4 equals 0. And so since I'm out of space, let me go up here. All right. Again, another quadratic equation. And this is one that's you should know by factoring. But if you use the quadratic formula, that's fine. You get the same two answers. Negative 4 times positive 1 is negative 4. Negative 4 plus 1 is negative 3. So you're going to get x equals negative 1 and x equals 4. Okay, so again, two answers. Quadratic equation, that's not surprising. But we should check. We should check, especially the negative 1 because, well, it's negative. Right? Now, that doesn't mean it's wrong. Right? You really have to be careful here. You can't just say, well, right, any negative answers are not allowed, right? And that's true. Right? That's true. But let's suppose that instead of the log of x, let's say it was the log of 2 minus x. If you plug that in, look what happens. You get 2 minus negative 1, which is the log of positive 3. There's nothing wrong with the log of a positive number. So right, you can see, even though x is negative, when you plug that in, you're not taking the log of a negative number. Okay? So that can happen sometimes. Just be aware that, just because it's negative doesn't mean it's wrong. Just because it's positive doesn't mean it's right either. Okay? Yeah. So let's just check the negative 1, and you'll see that, yes, that does not work. Right? So you get the natural log of negative 1 plus 4, so nothing wrong with that, minus the natural log of negative 1 minus 2. And we could stop there, of course, because this is the natural log of negative 3. And on the right, you have the natural log of negative 1. Both of those are just not allowed, right? They're undefined. So for that reason, we have to cross this out. Negative 1 is not a solution. Right. And I should give you a few minutes to check x equals 4. It turns out it does work, but it's not obvious, right? So yeah, you should pause the video and check it, but let's do it. So the log of 4 plus 4 minus the log of 4 minus 2, is that equal to the log of 4? Well, we get the log of 8 minus the log of 2, and yep, that's the log of 4. Now, if you're thinking, well, wait a minute, 8 minus 2 is 6. How do you get 4? Remember, quotient rule, right? This is not the log of 8 minus 2. It's the log of 8 divided by 2. And 8 divided by 2 is 4. That's a 4, which is certainly equal to the right side, which is also log 4. So log 4 equals log 4. That's correct, which means x equals 4 was the correct solution. And that's the only one, right? If you put negative 1, if you don't check negative 1, and you put that as an answer as well, it's wrong. And you're going to lose points for putting down a wrong answer. Right? Any more than if you put down x equals, 17. That's also wrong, as you can check. Okay. So again, I don't think they're going to get that much harder than this. Maybe we'll do one more. All right, last one for sure. natural log of 1/2 x minus 7 equals 1/3. Okay, so notice that there's nothing you have to combine here. This is just a single logarithm, and in fact it's natural log, so maybe we should write that as log base e in this case. Okay, right, so we're just going to use the definition, and just to remind you of that, right, log base a log, right, of n equals m converts to n is equal to a to the m. And so here a is e, n is 1/2 x minus 7, and m is 1/3. So kick the e over to the other side, and that knocks the 1/3 into the exponent of e. So this is e to the 1/3, right? Which is just some number. We can figure that out later, right? Now we just add the 7 to both sides. Right? So we have e to the 1/3 plus 7 on the outside, right? Right? Don't add the 7 to the 1/3. The 7 is not in the exponent, right? All right, and then just multiply both sides by 2. So that cancels the 1/2. So you get x equals, we can distribute the 2 here, right? So 2 e to the 1/2, e to the 1/3 plus 2 times 7 is 14. And again, that's the exact answer. But notice we also want you to approximate to 4 decimal places. So to do that, you simply have to plug this in your calculator. So let's do that now. Okay, well, my calculator, and I hope it's right, says this is 16.7912. Yep, 4 decimal places. Oh, hang on. Yep. Okay, so again, this is the approximate answer. This is the exact answer, right? But to get the correct approximate answer, you need the exact answer in most cases, right? Unless you approximated this right away, you could do that right away, but then all you're going to get is the approximate answer. In this case, we really want both, the exact and the approximate. And by the way, there's another way to write the exact. Remember, when you raise to the power 1/3, you're really taking the cube root of e, right? So this is 2 times the cube root of e plus 14, right? So you can do that on your calculator, or when you raise to the power 1/3 on your calculator, it's the same as taking the cube root, right? So I hope everyone remembers that, you know, a to the 1/3 is really just the cube root of a, although not the a is in the base, but just any a here. So I hope that helps. I think we solved quite a few of these, and again, when we get to the next section on applications, we're probably going to have to do even more.